That way, in case people miss this class. Okay, so now for example, if I say this is 2, and there's an asymptote here, okay? And we want to assume that there's asymptotes on the x-axis. And then we have a function look like this. Kind of familiar, right? Your previous test. How would you, what would you say? Let me quote this part. What would you say the domain is? Just verbally, how would you say what the domain is? What are the x's?
Yeah, everything except for 2.
Yeah, everything except for 2. Okay. What about y's? How many y's do you everything except for 0. Okay. So the way you write domains has to do with the x values, right? X's, right? And so this is a notation that you will write, and typically, and there are different forms of writing the domain. I'll give you the ones that you typically write in lower division math, and the ways for upper division math people will write. So the typical way would say, okay, it's all x's, and you can either verbally say all x's except x equal to 2. Okay, so that's one way to write it. Or you can say x is less than 2 and x is greater than 2, right? So it doesn't include the equals. There's no equal sign. But and oftentimes in this notation, people will write x colon like this. This is the notation for a domain. Okay? Colon means such as, such that, x such that. So that's the translation. Another way to do this is we can translate this into, so x is less than 2. That means x is between 2 and negative infinity, right? And you put a comma in between. Because it does not include 2, you put a parenthesis. Infinity is a non-destination. Infinity is not a destination. Infinity is a non-destination, so you put a parenthesis over there. And then n, you can just do a notation n. Again, x bigger than 2 is all the x values between 2 and positive infinity, because you don't include the bracket number. Then you put a parenthesis around it, and you can say that's domain. And the way you demonstrate domain is x column and not. Okay, range, same thing, very similarly. Range, these are y values. And you have said earlier, all y's except y equal to 0. So one would say, in a typical notation, one would say y such that, right? Y is less than 0, and y is bigger than 0. So that's one way to write it. Another way to write it is, you can say y such that, right? Y is less than 0, is between 0 and negative infinity, comma. You can put parentheses around it. And then equals, and then another one, which is 0 and positive infinity. So now you have domain and range. I'll tell you what I prefer. Although, you want to write any way you want, and all 3 options, fine. I prefer the last form of notation. Just because it's easier and it's transferable and you get the calculators, you still use that. Does that make sense? Okay, now I'm going to ask you to so here's an example, and I want you to tell me the domain and range. I'm going to sketch a graph. This is x and y. Let's see, let's make it up. -1, +3, 2, -2. Oh, not 2, no, let me just do this one. Just +2. So we got an asymptote here, an asymptote here, asymptote here, and I have a graph here. Okay, go ahead and write down the domain and the range. Domain and the range. Write it down. Write it down. What are the x values? What are the y values, available x values and y values for this graph? Again, remember I said that try to do it this way. Try to use this particular notation. Start training yourself doing that. Okay, check with each other. Check with the neighbor. See if you got it right. See what you got. Okay, then. Yeah, so basically you have three sets. So three sets of vectors. It doesn't do the so here's there's a good question that came up. Say for example, if you have x is less than x is greater than 2 and then is less than or equal to 5. How do you notate that? It will be 2 and a 5. Not equal will be a parenthesis. If there's an equal, it will be a bracket. Okay? Does that make sense? So bracket will be including that value. Parenthesis will be excluding that value. So that's just a side note. In case it's relevant to you. In this case, you probably won't have it because you're not going to include it, so you're not going to have the bracket page. Okay, so I'm going to move this a little fast along, so I'm not going to check on everybody's page. But x is, let's start with x, the domain, x such that, right? X such that you have three sets of x's, right? You have a x on this side, all the x's cover below -1, right? So it's -infinity and -1, parenthesis and parenthesis, because it does not include -1. There's asymptote there. And you also have x values covering between -1 and 3, but because you have asymptote on the negative x and asymptote on the 3, you do not touch other points. So you got negative 1, you got -1 and 3, but because they do not include -1 and 3, it's parenthesis instead of bracket. And then x is beyond that, so then you got 3 and positive infinity, so then you have a domain written this way. Okay, range has to do with y. Range has to do with y. So y in this case, y, it does cover everything below, right? So if you're scanning on this way, even though on this side of the graph doesn't have any of the y value, at least you have this graph covers all the y values from positive 2 all the way on down. So you got -infinity and 2, and then you got everything on top of the 2 except 2, right? So you got 2 and positive infinity. So there you go, domain and range. This is important because your radical function is going to have some, radical function is going to have like one side of the graph that has no value, right? So then you're going to have to be attentive to that. Sound good so far? Okay. So now I want to start talking about radical function in terms of graph. Okay, radical function in terms of graph. F of x equals square root of x. Now, this is also x to the 1/2. So I'm just going to go ahead and interchangeably use the radical form and the rational exponent form. That's function number 1 of f1 of x. So we also have f of x. This is the second one. Let me actually do it this way. Put 1 here. F of x, the second function, square root of x plus 1. And I suppose you can write it this way. You can say this is x to the 1/2 plus 1. We got, let me move it this way so person online can see it. All right. Okay, and then you got the third function. This has to do with square root of x plus 1. Right, so then the notation, the rational exponent notation will be x plus 1, the whole thing to the 1/2 power, right? You see the difference? You see the difference? Yeah. Hey. You see the difference?
Yeah.
Okay. I think a lot of times people, I pause to mention that because it's not in this class every year. For 25 years I teach math. I see students make their mistakes. If you need to see things. You've got to be very attentive to that, okay? Don't make mistakes on that. Okay? F of x, the fourth equation here. Square root of x minus 1, and this is equal to x minus 1 to the 1/2 power. And then lastly, actually not lastly, let me do a couple more. F of x fifth one, square root of 2x. This is obviously, this is 2x to the parenthesis, right? 2x parenthesis to the 1/2 power. And notice the comparing to the sixth function is 2 square root of x. Now 2 square root of x, this is very important. Take a look at the difference in the notation is 2x to the 1/2. Right, so this 1/2 right here does not apply to the 2. This 1/2 does apply to the 2. Get it? Yes. Yes, we're going to graph these. So we're going to graph these. So here's a question. Right? So all 6 functions over there is a very simplified version. There's nothing really complicated. It's really a variation of the square root of x. Right? So my question that I have for you is, what do all these numbers that added to the original function do to the graph? Right? So if I have a standard graph, the original graph looks like this. What do that extra plus 1 do to that original function? What do that plus 1 inside the root do to that function? What does that negative 1 do to the original function? What is the extra multiplier of 2 inside the x square root due to this function? And what does the 2 outside the square root due to that function? Get it? Make sense? What do you think will do? Just doing some in your head numerical analysis. What do you think will do to the graph? What do you think? Well, first of all, graphing the original function. Graphing the original function, say for example, just go into a very traditional like XY table, right? Input, output. So the easier first one is 0. You put 0 in here. Square root of 0 is 0. Okay, that's easy. Put 1 into here. Put into 1 here. Square root of 1 is 1. And the next one, I don't want to put 2 into x because put 2 into x square root of 2. I have no idea how to place square root of 2 unless I use calculator. But I know I can put 4 in here. If I put 4 as the input for x, square root of 4 is 2. So immediately I come up with that answer, right? Put it easy. Set up. Now, do I put negative 1? I put negative 1 in here, I get square root of negative 1. It turns out that becomes the imaginary number. Right? By the way, I won't get into it. If imaginary number, you say, oh, that's crazy, that's a mathematical imaginary number, an imaginary concept. Turns out that in actual reality, it's part of our reality. It's pretty wild. There's a connection between the real number line and the imaginary number line, and the connection is 0. That's a plural between the real world and the imaginary world. Turns out that it shows up in physics optics, shows up in quantum mechanics. Anyway, I won't talk about that. So undefined, right? Undefined in a sense, or imaginary number. Okay, so in this case, if you graph this, simply graph this, 0, 0 right here, 1, 1, 1, 2, 3, 4, 1, and 4 right here, 2 right here, to end up with this point, end up with a graph like this. It actually does not flatten out into an asymptote, it just keeps going up. So that's the base graph. So every time I look at square root of x, I know it's like, goes like this. Yeah. I'm just differentiating these are two different functions. But they're all f of x. F of x just means function. F of x means it is a function with respect of x. Meaning the function that determined by x's. Does that make sense? And when it's determined by x's, whatever this number turns out to be, that's the y value. Okay. Input, output. Okay. So this is a basic graph, right? This is the f of x equal to square root of x. So the question is, what does that extra 1 do to this graph? What do you think? This is a base graph, and with every single graph, every single number that we come up with on the original function, we just add extra 1. If we add extra 1, what happened to the graph? What happened to this? Shifted up, right? So you would imagine, or you would assume, right, without getting into numerical details, you would imagine that everything that would have been here shifted up to 1 value. So instead of 0, 0, it will be 0, 1. The starting point will be right here instead of right here. Right? And what would have been a 1, 1 would have become 1, 2, right? Would have been a 4, 2, 4, 2 right here. It would become 1, 2, 3, 4, 4, 3. So it would have become this way. So just shift it up 1 point. So if you do the analysis using the XY table, it makes sense. But you put 0 in here, it becomes 1. You put 1 here, it becomes 2. Right? If we put 4 in here, it becomes 3. Right? You just put it in there. Okay, that makes sense. So the question here is, then what will happen if this plus 1, instead of outside the root, goes inside the root? What will happen when this plus 1 goes underneath of that root, or inside the 1/2 exponent? What happened to the function? Who would guess? Who can guess? Yeah,
Its curve changes.
curve does not change, actually. What will happen is the same. What will happen? Shift it. Which way? To the right? To the left? Oh, to the right, to the left. Well, let's figure it out, right? So is it to the left or to the right? Okay, XY graph. Okay. If I put 0 in here, well, first of all, if I want to come up with a answer that's 0, it's very simple. I put -1 in here. -1 plus 1 is equal to 0. Square root of 0 is 0, so it's -1. That kind of gives me a clue already, right? It's like the number that gives, the output is 0, the input is -1. It's actually shifted to the left. Shifted to the left. So our starting point is at -1 right here. So I would imagine the next one, which would it be 1, 1, becomes 0, 1. So I'm going to venture to guess 0, 1. That would be our next point. So if I put 0 in here, 0 plus 1 is 1, square root of 1 is 1, so 0, 1. So I know, what would it be 4, 2, maybe 3, 2, it will become 3, 2. So if I put 3 in here, 3 plus 1 is 4, square root of 4 is 2. So I have 1, 2, 3, 2 right here. So the graph shifted. Graph shifted to the left. So if you add the 1 inside the root, you actually shift it to the -1, negative side. So that means if you can come up with that conclusion, this will be easy to guess, right? X minus 1, you know that it's going to shift horizontally, and this time, is it going to shift to the left or to the right? To the right. So this will be easy. This will be 1 right here, boom, like that. Easy stuff, right? So let me share this with you. Let me show this on the. Take a look at the what we have on the board. So this is our original graph, right? This is our original graph, right there. So I add another graph, f of x equal to, what's the next one? X to the 1/2. Whoops, that's not right. To the 1/2 plus 1. So as you can see, it's the green graph. Right? So it's the same graph but shifted up to the top. You guys okay? And then if you do this, the next one, f of x equal to parenthesis x plus 1 to the power of 1/2, right? It's the blue graph that shifted this way. And the next one, f of x equal to parenthesis x minus 1 to the power of 1/2. Right? So now it shifted this way, not this way. Okay, so now the question here, so when it goes in here, so we have two more to figure it out. So let's take a look at these. I'm going to get rid of all these other ones so we don't get distracted. We'll compare it to the standard one. This is our standard, which is the first one. So we want to look at the multiplier inside the bracket, inside the parenthesis. No, I'm sorry, inside the radical, what would that do? So f of x is equal to parenthesis 2x to the 1/2 power. What does it do? What happened? Stretch? What do you mean stretch? Make it taller, right? Right? Just close it up a little more, right? Close it up a little more. Makes sense, right? Because you got 2. 2 in here, 2 times 2 is 4. Square root of 4 gets you 1 faster than before. Because before it gets simply give you square root of 2. This time it gives you 2. Right? So you're a little bit faster. Now the next one. What about multiplier that is outside the root? What will happen? What do you think? Is it going to be faster? Is it going to stretch this faster than the previous one? Or a little bit smaller? But slower? What do you think? Multiply by 2 right away. Probably taller, isn't it?
Yeah.
Because before it was just square root of 2, right? Every number you got is inside the square root. This time is just whatever that one was. Well, let's see. I don't know if that's true or not, right? Because that's 2x to the power of 1/2. You see it? It goes faster. Yeah. Which one? This one, the second one, right? So this is the first one, square root of x. The second one is square root of 2x. The third one is 2 square root of x. The blue one. It goes higher. Grows faster. Right? So these multipliers basically allow your output to grow a little faster. Right? Questions on this? So next time, if I come up with a function, g of x is equal to square root of x minus 2 plus 5, and I ask you to graph this. Do you know how to graph this? Yeah. How would you graph it?
Take the original set of x and y values for the square root of x, shift it to the.
And you say, what does this 2 do to the graph?
It shifts it horizontally to the right.
To the right, two units to the right. And what does this 5 do to the graph?
It shifts 5 units vertically.
Vertically to the left, okay. So original graph would have been like this, right? That would have been a regular square root of x. This would have been that. Instead, this inside the negative 2 minus 2 inside the root is going to move it to the positive 2 steps. Positive 2 steps, and this phi is going to be 1, 2, 3, 4, 5. Phi right here. So this becomes a starting point. It's basically this graph, but start right here. And then boom, like this. So that's the graph, and that's what you will graph on the test to showcase the shift, the translation. Does that make sense?
Yeah, but it's not looking at x minus 4 plus 5.
Yeah, I can give you functions. Yeah. And I can even give you a multiplier so then it jumps up faster. Yeah. So then you actually don't have to depend on the graphical tool here, or you don't have to necessarily depend on this XY tables. You can quickly make a conclusion, and this will be really, really valid. Okay? Okay. Questions on this before I move on to the next section? Yes. That's right. That's right. But because if you look at this, the base graph is basically the square root of x. Right? The square root of x is right here. But because you got an extra negative inside the root, it has the effect of this. And because you have an extra phi outside of the root, you have the effect of this. And so you have to combine, and what I'm showing you here is basically how these extra elements on the function would do to the graph. And so if you have multiple elements in the same similar graph, you're gonna have a multiple movement. So in this case, you will move to the right and then move to the top. Okay. So I could give you another function, and I can say, oh, well, what would be f of x equal to, say, 2 times square root of x plus 3 minus 2, right? So you say, okay, this 2 is just a multiplier, so it will increase a little faster. Okay, I'll just make sure when I graph the final graph, I'll make it, go up a little faster. This plus 3, Vinny? For the root, for the square root. For the square root will always look like this. For the root, yeah, for the square root. For the cube root, different. For the square root, for the fourth root, for the 8th root, for the 6th root, anything that is an even number root, always going to be this way. Okay? And so then what happened with this? You basically, original graph, this plus 3 will make the original graph move which way? To the left by how many? 3 units. And then what about this minus 2? What will happen to the original graph? Move down by 2 units. Right? So then I can grab this real quick. This graph would be, can you see? I think this might not be easy to see. Let me just erase this part. This will be to the left 1, 2, 3, negative 3, and then to the bottom 1, 2, negative 2, and then go faster, like this. Okay, go like that. Okay, so then if we want to double check, let's share the screen one more time. Let's just get rid of these. F of x equal to, we got 2 parentheses x plus 3 to the power of 1/2, and then minus 2. Oh, look at that. Did I get it right? Did I get it right over there? Yeah. This one. Right? Of course, at the end of the day, You can always check with your calculator. But when you are really thinking through a lot of complicated concepts, you want to be able to immediately recognize in your head what that picture looks like. Does that make sense? You know, this is dating myself. You know, when I was in high school, we didn't have graph calculator. I had to go through a calculator, A, B, and B, C, all without graph calculator. So I had to be able to do this all in my head. Right? So I think there's advantage to that. It doesn't mean that you now, of course you can use your graph calculator, but what I'm saying is this, that now all of a sudden it makes sense. You see pattern emerge, and we'll be able to help you think through these problems. Okay, now I'm going to move on to the next section now. I'm going to go pretty fast, lightning speed. All right. I'm going to move this over here. I'm going to stop sharing. I'm going to focus on this board now. Now, so what we're doing right now, next one is 5.4, section 5.4, and we're solving equations. Solving equations, right? So we're solving equations, and these happen to be radical equations, right? Solving. So in this case, it's radical, right? Radical equation. Ready? Square root of x plus 5 minus 1 equal to 3. In this case, make sure I have enough time. So, in this case, the way the top part of this equation is because the radical is in a mix, and we know that radical is really hard to deal with unless we get rid of radical. And in order to get rid of radical, we have to square the radical. Right? Square the radical. But in the equation, you cannot just square it randomly. You got it, because it's an equation, you got it, whatever you do on one side of the equation, you got to do the same thing on the other side of the equation, materially, so that it doesn't tip off the balance. Right? But if you square the entire left side, it's a binomial square, right? If it's binomial square, the cross term is going to still have square. So that's not very useful for us, right? You understand what I'm talking about? Right? Binomial square, you have cross term, right? A plus b squared is equal to a squared plus 2ab. 2ab plus b squared. The a squared and the b squared will get rid of the radical, but the 2ab is going to keep that radical inside. Right? So you don't want to do that. So then the idea is you want to isolate the radical on one side. So isolate the radical, so then you just move the 1 on the other side, right? That's easy. So square root of x plus 5 is equal to 4. Okay? That's easy. So now, right, now you're justified to square on both sides. Square on both sides. When you square on both sides, you get rid of radical. So you got x plus 5, and this is 16. So then you end up with x is equal to 11. Now, when you do that, every time when you square or square root or do something to the equation on one side, on both sides, and you end up with an answer, you really have to go back to the original equation and see if the answer is correct, because you're in some way made a transformation of the original thing. Because this thing right here is not the same as the original equation, right? Because you square the whole thing. So whatever the answer that you end up with It may still fit the original equation, but it may not. We're not sure, so we've got to check. So you always have to check. Okay? So check with the original. You got to check with the original. So when you check it, you put the 11 back into x. So you got square root of 11 plus 5 minus 1 equal to 3. And you had to put a big question mark here. You don't know if that's going to be the case. It may be the case and perfect, and you got the answer. But it may not be the case. So in this case, you got square root of 16, which is 4. 4 minus 1. Okay, check. 4 minus 1 is 3. 3 is equal to 3. So I'm good. So the answer, I can keep this as the answer. Okay? It is possible that you may not get that. Here's real quick. I want to show this. And I think it's important for you to think about, especially for those of you who, let me just do it this way. In actuality, conceptually and graphically, we're saying there's an f of x equal to square root of x plus 5 minus 1, and there's a g of x equal to 3. There's two functions over there, and we're setting them equal to each other. Simply means we're finding, when we say equal to, then what we mean is we're finding the intercept point. That's the intersection point. So I can say f of x equal to x plus 5 to the 1/2 minus 1. Okay, remember this one? Negative 5 units over, and then negative 1 unit over. So I'm going to move this graph back again. You see that? Makes sense, right? The same translation. So now, we'll go to the next one. G of x simply equal to 3. Right here. So I'm looking at this point. Look at this. What's the x value of the intercept point? Between 10 and 12, what number is that? What if it's 13? This is 10, this is 12, and this is right here. That's 11, right? What do we have? X equal to 11. 11. That's what it means. When you have an equation, the way you think of it is, on one side of the equation is a function, on the other side of the equation is a function, and then they show up on the graph, and whenever they intersect, that is your solution. Yeah? All right, let's move on to this one. If this is a high endurance class, if you're feeling like you're a little bit unable to focus, stand up, stretch a little bit, and then sit back down. That's it. All right. Now, let's do this one. Square root of 3x minus 2 is equal to x minus 4. So I'm going to go ahead and show it to you. Instead of having you struggle, I want you to pay attention on this step. Not a whole lot different than what we did over here. Okay? So let's talk it through. Make sure you're with me. Okay? Make sure you're with me. You got a radical on one side, fully radical, there's nothing to do. So and we don't like radicals, so we can square that side, right? And we won't be dealing with the complication of cross term. So that's really good. That's a straightforward problem. You see that, you say, okay, I'm going to square both sides. So 3x minus 2. I suggest that it's better for you to write more steps than needed, just so that you don't get confused. Okay? So I square on both sides. So that's easy. Square root and square. The whole thing is, what's left is what's inside. And then on this side is a binomial expansion, right? A minus b squared. So it's a squared minus 2ab plus b squared, right? So it's x squared minus 8x plus 16. Yeah? So far, so good? You following? You with it? You with me, right? Now, what I noticed, yes?
So, the next step?
Yeah, next step. Yeah, go ahead.
You subtract the 3x minus 2, that whole thing, from the polynomial onto the other side. So it sets to 0, and then run that through the,
You can factor we can use quadratic formula, right?
yeah, quadratic formula.
So you'll notice that the natural step here is that you got a whole bunch of terms. You got some squares, you got some no squares, and all that. But you know that this becomes a quadratic equation. So you can move everything on one side to set it equal to 0. If you can set it equal to 0, then you know where to go, right? So move everything on this side, right? Subtract 3x. So minus 3x minus plus 2, minus 3x and plus 2 on both sides. Make sure you do that. If you're not very proficient in this, make sure you write these steps down. I'm writing more steps than I will usually do when I solve problems for your sake. Okay?
Oh, where's the 8x come from?
What?
The 8x. This is x squared minus 8x plus 16.
X minus 4 squared is x minus 4 times x minus 4, which is x squared minus 4x plus 16, x squared minus 8x plus 16. You gotta get this down, okay?
I just mixed it up and then I did.
Yeah, a lot of people do this. I still see goofy mistakes like this, really goofy. Goofy. Don't irritate me like this. Okay? Next time when I'm grading your paper, I get really irritated. don't make that goofy mistake, okay? Once or twice is okay, but don't do that too often. All right, now so you got rid of this becomes 0. So you got x squared, right? And negative 8x minus 3x is negative 11x, right? And then plus 18, right? Oh, I'm sorry, plus 18, plus 18. So then you can use quadratic formula, or if you immediately realize that you can factor this, right? You can factor this, right? 18 is 9 and 2, right? 18 is 9 and 2, 9 times 2. And 9 and 2, you add them together, it become 11. And 9 and 2, you want to get it to a negative 11, you got to have a negative 9 get negative 2. Right? So you got a negative 9 and negative 2. Good? I'm assuming you know how to do this, right?
Yes.
All right. just checking. So, well, I need a little bit more board space, so I'm going to put it right here. So I say, okay, well, that's cool. Over here, then, that means x minus 9 equal to 0, x minus 2 equal to 0, so x is equal to 9, and x is equal to 2. Wait, I had two answers. But remember, I said earlier, every time you're dealing with a radical equation, you're squaring on both sides, you fundamentally change the function. So you gotta check it. Yes?
What would happen if there were a similar equation in which the numbers did not come out to a factorable thing that added up into the 11?
I usually won't give you that kind of problem.
Yeah,
Because it would be one way to demoralize you. I won't do that. I usually will give you a question that will end up with a really nicely set up answers. I mean, there's a trick on how to write a test. I'll never give you a test that you will struggle to factor. Because the point is, I'm not here to test you how to come up with an answer. I'm here to test you whether you know how to get here and follow the steps to check it and actually show me conceptually you understand. Does that make sense? So I won't give you an answer where you have like decimal places to do it. So real function. Okay? But even if I do, even if the problem does show up where you have to use quadratic formula to come up with the answer, it still follows the same pattern. I'm just telling you that I'm not gonna waste your time and waste my time to give you a problem where you get stuck in such a trivial step. Okay, so here then you gotta check, right? Remember, you gotta check with the original equation. You gotta check it. So let's start with this one and then we'll go down with this one. This one first. Put this one going back to here. Not any of these that you have transformed, but original one. Gotta go back to the original. Okay, so you put that into here, you say, okay, that's 3 times 9 minus 2. The question is, again, remember, gotta put a question mark because you don't know if it's true. And then 9 minus 4. So I know that on this side it has to be 5. I want to see if that's true. Let's square root of 27 minus 2 is 25. Oh, 5 is 5. Yay! We got that one. We like it. Okay, next one. Square root of 3 times 2 minus 2. And then we don't know if it's the same as 2 minus 4. On this side, it is negative 2. On that side, that's 6 minus 2 is 4. So the square root of 4, that's 2. That's negative 2. They don't equal to each other. So this answer is called the extraneous solution. We don't have it. That shows up because we square both sides. Yeah, but we're not doing that. We're simply coming straight back into the original thing and see both sides. We already. Wait, what test?
When they're graded, so they haven't been graded.
Yeah. Hey, before you leave, listen up. There are still a few more examples from this section that I have not gone over. I will be making some instructional videos, and I'll share it with you on my cafe. And you'll get it probably later on tonight. And you'll be ready to review those with Mr. Chen tomorrow.
that'll do.
I think I may have. Let me